Hi class, in this recording we are going to be focusing on PhysioEx exercise number 5, activity number 7, how we compensate based on pathological conditions or disease states in our heart and cardiovascular system. As we look at this activity, there's some key terms that we need to emphasize. We can have our aortic valve stenosis, and as we look at aortic valve stenosis, another key term that I want you to focus on is also going to be atherosclerosis and arteriosclerosis. Aortic valve stenosis is when we have a partial blockage of the aortic valve. Aortic atherosclerosis is when we have an increase in resistance in our arteries, typically from the buildup of plaques within our arteries. And arteriosclerosis is when our arteries lose their elasticity. As we work through activity number 7, our scenario that is set up gives us the pulmonary circuit, pulmonary veins, the left ventricle of the heart, the aorta, and then our systemic circuit. So just like we had in activities 5 and activity 6. When you're done working through these activities, you had quite a big data table. And as we're looking at this data table, Ms. Laundridge and I weren't very pleased with it, so we cleaned it up for you and have it in this form. So in this form, for our data table, we have a baseline. Normal conditions are in black, aortic stenosis is in red, and then different ways to compensate are in different colors. We had green, orange, and we'll say blue for the 3 different ways to compensate for the aortic stenosis. So when we think of an aortic stenosis, that's a partial blockage of the aorta. A partial blockage of the aortic valve. So when we compare the aortic stenosis to the normal baseline, we find that there's a decrease in flow rate. And then as we look at this data table that we've cleaned up for you, the things that were unchanging, we left blank. So if there was no change, we left those parts of the data table blank so that you'd only focus on the things that were changing to make it easier for you to see the trends that were occurring. Let's make the screen a little bit larger there for us. There we go. So let's go back to our post-lab questions. We have our data. Question number 1 is asking, explain why a thicker myocardium is seen in both an athlete's heart and a diseased heart. And as we look at an athlete's heart, an athlete needs to increase cardiac output when they are exercising, so the myocardium is going to be thicker because they need to have increased cardiac output during athletic events. A diseased heart is going to have a thickened myocardium because it needs to increase the pressure gradient so that it can have increased cardiac output all the time. So hypertrophy of the heart due to athletics is not a bad thing. It's okay to have an enlarged heart if you're an athlete from exercise. But an enlarged heart because of a disease state is not a good thing. Those enlarged hearts never get downtime. Those hearts always have to work harder. And that's why hypertrophy of the heart due to a cardiac disease is not a good thing for you, because that disease state doesn't go away. The heart doesn't get a reduced workload. Unlike athletes who have increased workloads while they're physically active and then reduced workloads when they have their recovery times. As we look at afterload, this is a review term. Recall afterload is the back pressure, or the tendency of blood to flow backwards through the aorta into the left ventricle. An increase in afterload typically corresponds to an increase in peripheral resistance. Let's look at question number 3. Which mechanism in the simulation had the greatest compensatory effect? That's a $10 word right there. Well, let's look at the data. As we look at our mechanisms, we had increasing the preload, increasing contractility, and decreasing afterload. Increasing preload is another way of saying that we put more blood in the left ventricle. And as we increased preload in our heart, we find that as we have that increase in preload, we have an increase in cardiac output, and it increased to 4,400 milliliters per minute. As we look at increasing contractility of the heart, increasing the contractility of the heart is equivalent to having an increase in pump pressure, and that increase in contractility caused the cardiac output to increase to 4,600 milliliters per minute, and then decreasing the afterload, or decreasing systemic blood pressure or back pressure, also influenced cardiac output. As we had a decrease in our afterload, so our systemic blood pressure went down, the output increased to 4,600 milliliters per minute. So of the three compensatory mechanisms, increasing contractility and decreasing afterload were equal in being the most effective means for accounting for or compensating for an aortic stenosis, or a partial blockage of the aortic valve. Question number 4. Describe the mechanism used in the human heart to compensate for aortic stenosis. In our own human hearts, we have increased contractile force. Our heart will contract with more force to push blood past that partial blockage so that we can have cardiac output be maintained. So within a typical human heart, what we're going to see is we're going to have an increase in contractility. Decreasing afterload happens outside of the human heart. Increasing preload also happens outside of the human heart. The only one that we talked about that happens within the human heart is the increased contractility. That's all we have for activity number 7. If you have any questions or comments, please feel free to post them in the class discussion boards. And as always, happy studies.